Alright, for the last thing here on 2-2, we're going to talk about the intermediate value theorem. And what the intermediate value theorem is saying is that if I take some function and I look at the value of one point, and I look at the f value, the function value, that being the y value, and I decide down here that the y value is negative of that point. And then later on I find another point to the right of it where the y value is positive. We transition from a negative up to a positive. If we switch from a negative to a positive, we must have crossed the x-axis going from one to the other. If that's the case, that there must be a 0 in between those 2 points. That's what the intermediate value theorem is saying. And so if we know this, it helps us to find some of our zeros. And so we can use this here on example 6. Let the intermediate value theorem approximate the real zeros of x cubed minus x squared plus 1. And so this type of problem, we're going to go straight to the calculator. It's going to be the best way to do it. So let me bring up our calculator. Let me key in our equation. Go back to y equals x cubed minus x squared plus 1. And we could graph it, and it'll cross, and we want to know what this thing is. But what I'm going to do actually, and graph actually tells us that our 0 here is negative. Don't exactly know what it is. For the intermediate value theorem, I'm going to actually use the table here and let the table find it out for us. So I'm going to go to the table set here. It looks like our 0 is somewhere between -1 and 0 for the x's. So let's go into the table set and say, okay, we're going to start our table not at 0, but at -1. Let's count by point ones here. Alright, and as I scroll down, I'm looking for the point where I go from, in my y values, from a negative number to a positive number. Look at right there. Between 0.8 and 0.7, I transition from negative to a positive. So my 0 must be between -0.8 and -0.7. Look at that, there's delicious leftovers in the comments. Sorry about that, Emil. Alright, so now we know our answer has to be between -0.8 and -0.7. Let's go back into the table set and get a little more accurate. -0.8, and let's count by 0.01s. Where does it change in the y's from positive to negative? Positive, negative, positive, negative, positive. It's switching between 0.76 and 0.75. So we know that our 0 has to be between those 2 points. We could get even more exact if we wanted to. We could come back in here and say, let's start at -0.76 and count by hundredths. But to be honest, tenths, actually counting by thousandths, hundredths is probably the most accurate that you're going to need. We will jump in here, and so now we know that the answer is between 0.755 and 0.754. Okay, so that's what the intermediate value function theorem is asking you to do. Use your calculators, see if you can do it for this problem here, x cubed minus 3x squared plus 3. Alright, let me walk through the solution. We're going to go in here and let me take my window back to -10 to 10 just to reset. And it looks like I have a 0 here, here, and right here. So on this one, are we looking to find all of them or just one of them? Use the intermediate value theorem and the table feature to find the intervals 1 unit length in which the polynomial function is guaranteed to have a 0. So we're just going to need to find one of them. Let's find this first one over here, to the left here. This tick mark is a 1. I think it's to the right of the 1. I'm not exactly sure. Looks like it. Eyeballing it, it is. Graphing calculator could be wrong. So let's go from -2 back as our starting point for our table set. And let's count by point ones. We look at our y values. Where do we switch to a positive? There it is. We know that our 0 is between negative 0.9 and negative 0.8. We'll switch to negative 0.9 and count by hundredths. We transition from a negative to a positive in between negative 0.88 and negative 0.87, and so we'll go with that. We'll approximate our 0 at negative 0.875, halfway in between the two. Alright, that's it for 2-2. If you have any questions, please let me know.